Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlist. I'm using this playlist to help lecturers, tutors, high school and primary school teachers, parents and students with any mathematical problems or concepts that they're having difficulty with. So if you'd like me to make a video for you or your students, use the comment section below the video. Okay, we're halfway through the 4 steps to show that any integral domain can be embedded in a quotient field. So in the first step, we showed how to construct a nice, proper mathematical set that we can use as part of the field. In the second step, we showed how we can construct the operation of addition and multiplication, which work, and we showed in a rigorous mathematical way that they work for the fractions. So now we go to step 3, and remember, in everything I'm saying, I'm just using the term fractions and integers, but you can just substitute integral domain for integers and quotient field or field for the fractions. Okay, so this is where we've got to. The rationals or the fractions are with the question mark, because that's what we're establishing. So far we've established this is the set that we need, and these are the 2 operations. So we have to show now that this Q, the fractions, are a field. And to do that, we have to go through all the steps that I went through in one of my previous videos. There's a whole lot of axioms or rules that you need to check for fields. So what I thought I'd do is I'll do one of them and properly, and then I'll make some comments on the others. So here's one that addition in the fractions is commutative. If we don't have that, we don't have a field. Addition is commutative. And remember, commutative just means we can change the order when we add, in this case, when we add. And we know that with fractions, you can change the order of addition. So that's all I'm actually proving. But the thing here is to see it in the sort of language and notation that we use here rather than we would in primary school. So let's create 2 fractions. Remember, we're using equivalence classes, and an element of the equivalence class is an ordered pair. So this is actually the fraction AB, and we're going to add CD. Actually, I wonder if I could do it this way, which would be cute. I'll write here what I'm doing in normal sort of notation. Okay, what's that? Well, this is equal to AD plus BC times BD, comma BD. That's the ordered pair. So I'll put equal there. And now I'll go over to here and I'll say AD plus CB on BD. Okay, this is quite cute actually. It's quite nice. Now the next thing we need to realize is that, remember, all of these are in integers, just the numbers 5 and -7. So I'll put here, since the integers are an integral domain, we have well, this AD here, AD is DA. Is the same. BC equals CB. Maybe I've been a bit sloppy here. AD plus BC and BDA, yeah, that's okay. AD, actually, let's check. Let me just check. Let me just change this. I've got that in the wrong order. Although I mean, this is the point, it doesn't really matter, but AD BC. Okay. So here we've got that AD equals DA, BC equals CB. Whoops. Equals CB, and this one here, BD, equals DB. So what would we say here? I suppose if we were doing it in primary school type language, we'd say because A, B, C, D are integers, A times B equals B times A. B times C equals C times B. B times, whoops, B times D equals D times B. Well, the other thing that you might see, they might say at school is just do it by example. 7 times -3 equals -3 times 7. You just say, well, that works. We've seen how that works in our previous year at school. So that's what we're doing. Okay, so now we can go on. So we're going to go back to this now. We're saying that this, so AB plus CD is equal to, I can just change the order around because I've explained now why I do that, DA plus CB, comma DB. I might have to do it again. Now, is that CD? I think we might have to do another change of this around as well. Let's just have a think about this. What I need to do is end up down the bottom. This is a good trick in mathematics. I've got to end up with it round the other way, I know that. So I can go back a step. What would tell me that? Well, that would tell me that A times D, so that would be CB, whoops, C times CB, yeah, well, hold on. CB plus DA times DB. That should be fine. So remember when we went up here from this step to this step, we've got to ensure that this is the same as going from this step. So the A goes there, the C goes there. The B goes there and there. Oh, sorry, the D, what are we doing here? The first term goes, the first term here is C, goes to the first term, which is true. The second term, so up here, the second term goes to this bit and this bit. So the second bit goes to this bit and this bit, yep. The third term goes to the second term there. The third term goes to the second term there. Yeah, so that seems right. So what you can see here is I've used the same concept here. I've just said that I can swap DA and CB. CB and DA, DB stays the same. So that would work there. So that's probably good enough. And well, good enough, it is good. So what I'm saying here is that A on B plus C on D equals DA plus CB on dB. And then you just finish it off like that. So that's the basic idea there. This, I think, is okay. I'll leave you to finish off I'm not sure how the primary school one would work out at the end, but something like that. Now, just in this, I'll just make a few other comments quickly. Identity element for addition. Is 0, 1. Yeah, because if you work through, if you add this on to anything, so what I'm saying is that AB, we take any fraction plus 0, 1, when you work it all out, you just get AB. When I say all AB, I'm not worried here about the fact that B can't be 0. That's incorporated, that'll work. And then we have inverse under addition. So, AB inverse is, I suppose, negative AB. When you add these two together, you'll get, so let's do that, AB, whoops, AB plus negative AB equals 0, 1. And then there's going to be a multiplicative identity, multiplicative identity, which is 1, 1. And you can see that AB, if you work through the rule for multiplication, that times 1, 1 equals AB. And then there's a multiplicative inverse, which is the inverse of AB. Put the inverse equals B on A. And if you look through Freilich or any similar sort of thing, you'll see how all the stuff in terms of B not equaling 0, you can't have a fraction with a 0 as the denominator, all sort of works out. So I think that's all I want to say in step 3, but if you've got questions about it, obviously just comment below and I'll expand a bit more on it. Okay, and so any questions on anything in mathematics as well, just comment below and I'll try and help you out.